In this video, we're going to take a look at various array attributes that help you learn information about an array object that you're manipulating. So once again, I'm going to import the NumPy module as NP, and let's start by creating a couple of array objects. So here we have an integers array, which is a two-dimensional array with 3 elements in each row. So we'll create that and just take a look at it. And separately, let's also create our first floating point array object. So as you can see here, we have a one-dimensional list that we're handing it, and the values 0.0 through 0.4. And if I go ahead and display that, you can see the formatting for a NumPy floating point array. Now I do want to point out that by default it does not show trailing zeros. So 0 point is how it represents 0.0 by default. Also, once again, it is going to format the floating point numbers with the same number of character positions to enable alignment in multi-dimensional arrays. So here we've gone ahead and created a couple of arrays. Now let's take a look at what the data type is for each of these arrays. So it turns out that for each array object there's a dtype attribute, and if you invoke that on the integers object, you can see that by default it has a data type called int64. Now this is one of many NumPy data types. NumPy is actually implemented in the C programming language for performance, and each of the types that you work with in the context of Python actually winds up getting mapped over to a C data type underneath the hood for performance reasons. Now by default, when we're working with integers, we're going to get 64-bit integers underneath the hood in the context of NumPy, and similarly if I go over to my floats and do dtype on that as well, you can see that we get 64-bit floating point numbers as well by default. Now I'm going to take a temporary diversion over to the documentation for NumPy. This page that you currently see displayed on the screen is where you can find all of the data type information for the underlying types that are stored in NumPy arrays. So I'm not going to go through this page in detail, but if you are interested in all the different data types that are available to you, you will want to go ahead and take a look at this web page. Let me switch back over to my terminal window. The next thing we want to do is take a look at how to determine an array's dimensions. And it turns out there's another attribute that you can access for that purpose. So let's go ahead and use the ndim attribute, which stands for number of dimensions. And for the integers object, remember it was a two-dimensional array, so we get 2 as the result. And if I say floats.ndim, you can see that we do in fact get 1 as the result for that. You can also look at what they call the shape of an ND array. So if I go ahead and say integers dot shape and press enter, you can see what I get back is a tuple, which tells me how many rows and columns there were in that two-dimensional array. So 2 rows and 3 columns per row, and again you can see 2 rows here, and each row has 3 columns. By the way, that is a difference between NumPy arrays and two-dimensional lists. In a two-dimensional list, each row can have a different number of elements. In a NumPy array, all the rows have the same number of elements. So let's also take a look at the floats array and look at its shape. And as you can see, we still get a tuple back, but it's a 1-element tuple, indicating that the one-dimensional array has 5 elements in it. So when you're doing multi-dimensional arrays, you get the number of items in each dimension, so 2 rows and 3 columns for the integers array. But when you do a one-dimensional array, the tuple is a 1-element tuple that has just the total number of elements in that one-dimensional data structure. So the next thing we want to take a look at here is determining an array's number of elements and element size. So if I say to the integers object, tell me what your size is, I get back 6, which is actually the multiplication of the number of rows times the number of columns. So 2 times 3 gives me 6 total elements. And I can also go ahead and check the item size, which is how many bytes are being used to store each element in the integers array object. Now in this particular case it is 8, but this is actually going to be dependent potentially on the underlying C compiler that was used to compile the NumPy library in the first place. So we saw up above that we had 64-bit integers, which is an 8-byte integer, and therefore the item size returns 8 in this case. Now of course we can also look at the float array's size. Whoops, floats.size, there we go. And we have 5 as the total number of elements there, which is correct from the way we defined the array back at the top of the screen here. And then separately, let's go ahead and check its item size as well. And you can see that the size for the items in the floats array are also 8 bytes each, and that makes sense because we had float 64 as the default type of that array. So at this point we've looked at a number of different attributes. I just also want to show you briefly that we can iterate through arrays just like we can iterate through lists. So let me paste in a snippet here first and then we'll execute it in a moment. Here we have a nested for loop that is going to walk through the integers array. So for each row in the integers array, we're then going to iterate through every column within that row. And for each item that we're dealing with, we're going to display the column's value followed by a couple of space characters. Now, I don't really need to do this because if I just evaluate integers, it's going to give me a nice two-dimensional representation of the integers array. In fact, going back up here, we can see what that looks like. But let's go ahead and execute this. After the inner for loop ends, we'll just display an empty print, which will just output a new line character to drop to the next line and start the next row of output. So there's our 2 rows of output with the integers 1, 2, 3 in the first row and 4, 5, 6 in the second. Now, one interesting thing that you may find the need for at some point is you can iterate through a multi-dimensional data structure as if it's a one-dimensional data structure. So let me paste in another code snippet here. We have the flat attribute of the integers object, and what that does is it says to flatten out the multi-dimensional integers array, and in the case of integers we had a 2-row 3-column array. So what happens is it after the first row, it basically takes the second row and sticks it at the end of the first row for iteration purposes. Or if we had 10 rows in 3 columns, it would go row by row and just keep adding them to the end in terms of enabling iteration through the data structure. So in this case, if I go ahead and execute the for loop, because I'm doing it through the flat attribute, it gives me back the integers as if they're just one long one-dimensional sequence of integers in this case.